All right, guys, we're going to go ahead and finish up our notes for intervals of increasing and decreasing today. Did just want to kind of review this process that we go through. So first off, we know from last unit that when we're talking about when a function is increasing and when it's decreasing, a function is going to be increasing when the first derivative is greater than 0. It is decreasing when the first derivative is less than 0. So like the big idea when I ask you to find the intervals of increasing and decreasing is we want to be able to look at the sign of the first derivative. So the steps that we're going to go through is we first need to find something called the critical points, which is something we defined yesterday. The critical points occur in two places on the graph. The critical points occur when the derivative is equal to 0, and then the critical points also occur when the derivative is undefined. As a shortcut, if it helps you out, especially if you have a derivative that's like a rational expression, so it has like a numerator and a denominator, when the first derivative is equal to 0, that's going to occur when the numerator is equal to 0, and then the derivative is undefined because we can't divide by 0 in math when the denominator is equal to 0. So we will solve those two equations. Again, not every derivative is undefined. Maybe not every derivative is equal to 0. But once we find those critical points, we can use them to create a sign chart. And the sign chart, just to remind you of the example we did yesterday. So we had the function, we found its derivative. It didn't have a denominator, so we only needed to find when the derivative was equal to 0. Factored answers are going to be the easiest ones to deal with for us. So we factor it, and we find that it is equal to 0. In this case, it was 3 places. And so on the sign chart, there's kind of 2 things we need to do to set it up. On the vertical column, you're going to list all of your factors. And then along the top is a number line with your critical points. And you just need to figure out when it's positive and when the derivative is negative, and then use your answer and then justify it correctly. So the ones that we're going to look at today, I think, are the ones that are a little bit trickier. So most people don't have issues with like ones that are polynomials. They're very straightforward. Ones that I think are trickier are ones dealing with trig. So there are some things I just want to point out for a trig problem. The first thing is when you have a trig problem and it's asking for intervals of increasing and decreasing, it will always give you an interval. So you're never going to have to go back to like negative infinity or forward to positive infinity, because trig we know is periodic, so like it's going to just repeat itself over and over and over again. So like there'll be like literally an infinite number of intervals of increase and decrease. So the domain will be restricted. And so the first step we're doing, like if we talk about intervals of increase and decreasing, we know we need the derivative. So let's go ahead and just find the derivative. And I have f prime of x is equal to, so the derivative of 12 is 0. The derivative of 4x is 4, minus 3 is a coefficient. The derivative of tangent is secant squared of x. So the issue with trig, one, like big issue is some people just are bad at solving trig equations. But in terms of like the calculus of it, trig can be a little bit tricky because there's often like hidden denominators where the derivative is undefined. So you do need to be careful about hidden denominators with certain trig functions. The ones that have hidden denominators that you just need to be aware of are like the reciprocal ones of secant and cosecant, and then also the quotient ones of tangent and cotangent. Because we know that the derivative is undefined when the denominator is equal to 0, so we want to make sure that we can clearly see what that denominator is. So looking at this one, even though we don't see a denominator in it right now, we know secant squared has a denominator. What's another way we could rewrite secant squared? 1 over cosine squared. So my derivative, I can rewrite it as 4 minus 3 is the coefficient. I can send that secant squared to the denominator as cosine squared. And then the other kind of tricky part that we need to remember is, so we have the hidden denominators to worry about, and then also when it comes to a sign chart, writing it as a single fraction is going to make your life easier. So we want to be able to, I'm going to reword that differently, write as a single fraction. And what I mean by that is we often need to find a common denominator. So like this equation is one you can solve, like you could set it equal to 0 and get an answer. But this one is not a nice one to make a sign chart with, because technically right now we have no factors. This is being subtracted, so there are two terms. So if you made a sign chart, it would just have one row. And this is a pretty complicated one to make a sign chart with. To make it easier, we can find a common denominator. So that 4, we can think of it as 4 over 1. Common denominator is going to be cosine squared. So I'm basically multiplying that 4 by cosine squared over cosine squared. And that way we're going to have a much more friendly denominator, but also much more friendly first derivative. So I have 4 times cosine squared minus the 3 and a common denominator of cosine squared. These two derivatives are exactly identical. I know that one in orange looks simpler because there's no denominator, but hopefully you can agree with me that like cosine is a lot easier to deal with than secant. Also, the idea about having like these fractions is going to make a sign chart a whole lot easier to do. So we've done the first step. We found the first derivative. Once we find the first derivative, what do we need to do next? Set it equal to 0, and we also need to figure out where it's undefined. So don't forget that place. So we have our critical points, and the critical points occur in two different places. The critical points are going to occur when the derivative is equal to 0. They're also going to occur when the derivative is undefined. Some people accidentally forget that second part. So when I say when is this derivative is equal to 0, that's going to be when the numerator is equal to 0. So we don't really need to worry about the denominator right now. That just becomes a regular trig equation to solve. Same thing for the other side. Where is this derivative undefined at? This derivative is undefined when the denominator is equal to 0. And then hopefully this looks very much like some stuff you did last year in pre-calculus. So I go ahead and solve it. I'm going to solve this second one because it's easier. Take the square root of both sides. So cosine of x is equal to 0. The other one, I'm going to add 3, then divide by 4. So cosine squared of x is equal to 3/4. Taking the square root of both sides, I get plus or minus the square root of 3 over 2. Square root of 3 is just the square root of 3. Square root of 4 is going to give you 2. Don't forget the plus or minus. And then this is where the restricted domain is nice. So sometimes we're going from 0 to 2 pi. This one we're only having to go from 0 to pi. So I only need to find critical points within that interval. So let's do cosine is equal to 0 first. Thinking about the unit circle, cosine is equal to 0 from 0 to pi, just at pi over 2. And then we want to think about when cosine is equal to plus or minus root 3 over 2. Those are going to be the ones that are lower in the unit circle. So we would have critical points at pi over 6 in the first quadrant and 5 pi over 6 in the second. So this graph does have 3 critical points. Again, those critical points are important because those are potential places on the graph where it can change direction. Like it might change from increasing to decreasing, or it might change from decreasing to increasing. Or it might just not do anything, but there are some sort of key points on the graph. So I found my derivative. I rewrote it so it was friendlier to use. I found my critical points. What do I need to do next when I'm doing intervals of increasing and decreasing? Sign chart. Again, there's lots of different ways to do sign charts. I kind of have my way of doing them. Not the only way to do a sign chart, but I do think my way is kind of the best way, just from teaching it different ways over the years. So remember, on the sign chart, the vertical part is going to be your factors. In this one, your factors are just going to be the numerator and the denominator. So we have 4 cosine squared of x minus 3. And then I have cosine squared of x. And then we put our critical points along the top, making sure you put them in order, because it is acting like a number line. So pi over 6 is the smaller one, then pi over 2, and then 5 pi over 6. One other thing I add just for these problems, since we are restricting the domain, I don't want to accidentally include like negative infinity or positive infinity. So I'm just going to put a reminder to myself that we're starting at 0 and ending at pi. Those aren't critical points, but I just like doing that as a reminder for myself. And then I also add, remember that vertical bar that goes where the critical points go with a certain factor. So for example, that numerator gave me pi over 6 and 5 pi over 6. Those will be the only times where it can switch signs. Cosine squared gave me pi over 2. So the only time it could possibly switch signs would be at pi over 2. So now we just need to think about these points and think about when it's positive and when the derivative is negative. I'm going to do the easier one first, cosine squared. What is cosine squared going to be? Is it ever going to be negative? No, like if you square something, it's always positive, so it doesn't matter if you plug in something less than pi over 2 or greater than pi over 2. Cosine squared is always positive. So that makes that part of the sign chart easier. I think more people have issues with the first factors. So we have 4 cosine squared of x minus 3. Again, you want to think of plugging in radian values. I would choose like some easy ones. One hint I can give you, so you can't plug in the critical values that came from that factor. So I couldn't plug in pi over 6 and 5 pi over 6, but you can plug in like 0, I can plug in pi over 2, and I can plug in pi, and those tend to be really easy values to deal with. So just kind of show you, like at this first one, I can think about what is 4 times the cosine squared of 0 minus 3. Well, the cosine of 0 is 1. 1 squared is 1. 4 minus 3 is definitely 1, so that is greater than 0. So I know that this interval is positive. And I can kind of repeat that for the middle one. I'm allowed to plug in pi over 2. So cosine squared of pi over 2 minus 3. The cosine of pi over 2 is 0. 0 minus 3 is negative 3. That's less than 0. So this whole piece is going to be negative. And then I can go ahead and plug in pi. It's going to kind of cheat. The cosine of pi is negative 1, but I'm squaring it so it becomes positive 1. So it's going to be the same thing as that first interval. So then I can figure out what the interval is overall. This first interval has a positive divided by a positive, so it's positive. The second interval is a negative divided by a positive, so it's a positive. Then I have a negative divided by a positive again. I don't know, I wrote positive. Let me rewind and try that again. Negative divided by a positive is definitely a negative. There we go. And then again, negative divided by a positive, definitely a negative. And then a positive divided by a positive gives you a positive. We haven't done the answer yet, but we are going to pause and just see if anyone has any questions on all that work, because there's a lot kind of going on that screen. Mitchell.
So the interval is between 0 and 5. So
yes.
That would include 3 pi or 3.
So yeah, we're not going to do anything beyond pi. And you want to be careful, like when you're plugging in test points. Like I chose pi here because it was the one closer to 5 pi over 6. If you end up plugging something like 3 pi over 2, that's like beyond the interval and like a whole different, past like a different quadrant, so you can end up messing up the sign of that last interval. So I tend to like plug in the endpoints when I need to, as long as they also aren't critical points. So then we can go ahead and answer the question. So remember, when you answer the question, the sign chart is just kind of your work in calculus. Even though it's a math class, we just kind of have to be able to get used to writing our answers out. So to justify my answer, I'm going to do the intervals of increasing first. So this was f of x. So I can say f of x is increasing on the interval from 0 to pi over 6. And then it's also increasing from 5 pi over 6 to pi. How do I know that it's increasing there? Because that's where the first derivative of x is greater than 0. And then I also know that f of x is decreasing on an interval. It's decreasing on the interval from pi over 6 to pi over 2, union pi over 2 to 5 pi over 6. How do I know? Because the first derivative of x is less than 0. One last thing I want to say, I don't want to confuse anyone, but since this has two intervals in a row that's decreasing, it would be okay if you said it was decreasing from pi over 6 to 5 pi over 6. I don't like that way because technically what's happening on this graph, pi over 2 is an asymptote, so like there is no graph there, but that would not be marked wrong if you listed it as an answer. But I think the first way is just nicer because it just more clearly matches your sign chart. And again, we can do this all without looking at the graph. In fact, normally you wouldn't have a calculator for a question like this to check your graph. Just for the sake of looking at what the graph looks like, and I'll kind of take questions. I can graph this one. If I can get there. So I'm just going to use Desmos and graph it just so we can kind of check your answers, just so we can kind of see that the calculus does work. So f of x was equal to 12 plus 4x minus 3 tangent of x. Looks like a crazy graph, and I'm going to count these x's by pi. Oh, wrong one. Go. And we were looking at the interval from 0 to pi. And it's not the best scale, but you can kind of see this little dip of what we have. 0, we can see like it's like increasing, then decreasing. It goes down a whole lot, and then start increasing again as well. So like you can kind of see where calculus is nice. When you have like these graphs that really are just crazy, we can at least trust our answer because we know what the derivative means in context. So that's where we're going to stop today's notes. Like I didn't really have too much to do to finish up the notes. Tomorrow we are going to be looking at intervals of concavity, which like short answers, the exact same steps, but instead of using everything with the first derivative, you're going to do it with the second derivative, so like sign chart and all that. So it really won't be that new tomorrow. I just think the second derivative just has more algebra because you have to do the derivative twice. So it would be really great just for practice if you could finish homework 1 today. Again, the homework is not due until the day of your quiz, but I think finishing that first homework, or homework 2 I should say, will definitely help you out. So looking at where you should be at, so homework 1, if it's not done, make sure you ask them questions on it if you have it. Homework 2, you should be able to do all of it at this point, including the trig ones. Tomorrow we're going to do concavity, and Friday we'll do concavity as well. Friday is going to be a review day, and then your quiz is going to be that awkward Wednesday between the 2 weird days that we have. So yeah, so for the rest of class, y'all can go ahead and get started on what you need to get started with. Definitely let me know if you have any questions, whether you're at home or in person. And yeah, that's it. So y'all can go ahead and get started. I'll just kind of walk around and answer questions as I have it. Or if you're at home, just kind of virtually raise your hand and I will come help you as soon as I can.